Hello and welcome to the next lecture in this course on pattern recognition. We have been discussing the non-parametric density estimation techniques. As I said last class, in the non-parametric method of density estimation, we do not assume any functional form for the density. In the parametric density estimation, we assume a particular form for the density function and then estimate the parameters, whereas in the non-parametric form, we do not assume any form for the density function, and still we need to have a density estimate. As we discussed last class, the basic idea is generalizing a simple histogram for the density estimation. So, the basic idea is to estimate the density value at a particular value x as represented as f hat x to be equal to k by n times v, where v is a small volume element, a small element of volume v put around x, in which out of the n data samples we found k data samples. As we discussed last class, this is a reasonable estimate if k out of n samples are found in this volume. Essentially, if we are assuming around the small volume density is constant, then this is a good estimate for the density. So, the estimation, our final estimate is k by n v, where v is the volume of the small region around x that we chose and k is the number of data samples that are found in that region, while n is the total number of data samples. Okay. As we already said, the choice of the volume element is critical for getting good estimates. If it is too large, then we get very heavily smoothed out density estimate, which is not accurate, and if it is too small, not many data samples will fall there. So, most of the places the density estimate may become 0. Okay. So, the choice of v is quite critical in non-parametric density estimation. And we discussed in last class that there are basically two possibilities in getting this kind of density estimate. By this kind, I mean f hat x is k by n v kind of estimates. The two possibilities are, one is at each x we fix v. So, at each x we take a region of volume v around x and then compute k, the number of samples that fall in that region. These are called kernel density estimates or Parzen windows. And the other approach would be to fix k and compute the needed region to enclose the k samples and compute its volume. Okay. These are called k nearest neighbor density estimates. In non-parametric estimates, mostly one uses only kernel density estimate, most of the time only kernel density estimate when we want an explicit density estimate. But k nearest neighbor density estimates are also used in a sense to justify nearest neighbor classification rule, and also they are used in certain regression estimates. Okay. We will consider both of them in this class. Okay. Now, let us first look at the Parzen window technique. Okay. So, for this we will first define what is known as a window function. Okay. So, let us define a function phi, which we think of as a window function. It is a function from R d to R, where d is the dimension of the feature vector, or feature vectors are in R d. So, we define a function R d to R by phi of u is 1 if u I, each component of u is its absolute value is less than 0.5 is 0 otherwise, right. So, u is the vector u1 to ud. As I already said, we do not put any bold notation vectors. So, from context. So, this u is a vector, okay, and its components are ui, and phi u is 1 only if each component is in absolute value less than 0.5. So, what does this give us? This defines a hypercube in R d centered at origin, okay, because it is a unit hypercube side of side 1. That is why for ui between minus 0.5 to plus 0.5, if all I for all I ui is between minus 0.5 to plus 0.5, then phi u is 1, otherwise phi u is 0. So, this phi u is essentially a indicator function of the unit hypercube in R d centered at origin. That is to say, if the point u is inside the unit hypercube in R d centered at origin, then phi will be 1, otherwise phi will be 0. Okay. We also note that because they are centered at origin and the way it is defined, phi u is symmetric, phi u is phi of minus u. So, if I do a translation and scaling of phi, then phi u minus u 0 by a translation would be a unit hypercube centered at u 0. So, phi u minus u 0 by h will be a hypercube of side h centered at u 0. Okay. Now, let us say as usual x1 to xn are the data samples. Then for any given x, that is any point in the feature space, phi of x minus xi by h would be 1 only if xi falls inside an hypercube of side h centered at x. We just seen that phi is symmetric. So, when you consider phi x minus xi by h, I can think of it as a hypercube centered at xi or centered at x depending on which I am fixing. So, for any particular value of x, phi of x minus xi by h can be thought of as a hypercube of side h centered at x, and hence it will be 1 only if xi is inside this hypercube. Okay. So, this function essentially allows me to ask which of the samples are within a hypercube of side h centered at x. So, if I take the volume element to be hypercube of side h centered at x, then this is how I can count how many of my samples fall in this volume element. Okay. So, that means the number of data points falling in a hypercube of side h centered at x is given by sum over I is equal to 1 to n phi of x minus xi by h. For each I, phi of x minus xi by h is 1 if xi is inside this hypercube of side h centered at x. So, this sum will give me the number of points in this hypercube. Okay. And in R d, a hypercube of side h has volume h power d. So, now we know the volume element h power d, we know the number of points that fall in this volume element, and n is the total number of data samples. So, we can write our estimate f hat x as sum over this phi x minus xi by h is k, k by n v is what I need, k by n and v is h power d. We will write it like this because it is a more convenient form. So, it is 1 by n summation I is equal to 1 to n 1 by h d phi x minus xi by h. As a matter of fact, this should remind you of the mixture density model that we considered a couple of classes ago, right. It is a mixture density and I will come back to that later, but given this window function phi, if I wanted to do my estimate as k by n v that we discussed earlier, this will be the expression. So, I can use this phi function to actually find the density value at any x. Okay. So, this is known as the Parzen window estimate. Okay. Essentially what it means is that when I want density estimate, what do I need density estimate for? To implement the Bayes classifier. So, to implement the Bayes classifier, when I need see a new feature vector x, at that x I have to compute the value of the class conditional densities. So, if I store all my samples xi given any x, I can compute phi hat x using this. Okay. The value of h determines the size of the volume element. We said we have to take some volume of appropriate size. So, that choice is now translates to choice of h. So, I choose some h and then given any x I compute this, that will give me the density estimate at x. Okay. So, Parzen window density estimate is given by this. I hope one can see there is a kind of generalization of the histogram idea. We take a bin and count a volume bin and count how many data points fall in that volume bin. Okay. Only thing what we are doing is we are erecting bins where we need. So, I need to estimate the value of x, density at a particular given feature vector value x. So, I only need f hat x at that x value. So, as and when I need it, I compute this by keeping all the xi with me, and the size of the volume element is controlled by the choice of h. Okay. Essentially, the reason for writing like this is to say that the counting can be done by a function phi. We have chosen of course the unit hypercube for this function, but there are many other functions that are feasible, right. So, I can choose many different volume elements, so to say, and actually we can even generalize this to say that it is not actually a volume element with very discrete boundaries. So, we look at if I want something like this to be a density estimate, what kind of property should phi have, and then by choosing any such phi we can get a similar estimate. All such estimates are called kernel density estimates and sometimes also called Parzen window estimates. Originally only the hypercube estimate is known as Parzen windows, but generally any permissible phi when you use it is generally called as a Parzen window estimate or a kernel density estimate. So, let us ask what are the properties that phi should satisfy. Essentially we are only using for this to be a density estimate, we only need two properties of phi. One is that phi should be positive, and two, integrated over R d, phi should integrate to 1. That is to say, phi should itself be a density. The reason is the following: if phi satisfies this and we choose the volume that V in the denominator of my f hat to be this sum over integral over d phi of u by h, because this integral is over all R d, a translation does not make any difference. So, integral phi u by h du is same as integral phi u minus u by h du by, you can simply put u minus u 0 is equal to u prime, then du will be du prime, integral will still be over R d. So, if a function phi satisfies this and phi u by h du integrated R d is V, then this density estimate with this 1 by h d replaced by 1 by V would be a would be a proper density. For our particular hypercube window function, V has turned out to be h power d. That is why we got that particular form for the Parzen window estimate. But in general, as long as I define V by this quantity, then this will be a density. Why is this a density? Because by this definition of V and the properties of phi, this 1 by V phi x minus x I by h will integrate to 1 over x, right, and I am summing n of them. So, it will become n, and divide by 1 by n it becomes 1. So, essentially if I use this, then f hat would be a density, that is f hat would always be positive because phi is positive, and f hat x dx will be 1 because the way I define V and the properties of phi would ensure that each term here integrates to 1. We can choose any now that we understand that this is what we want out of our phi, we can choose many other phi functions and correspondingly calculate the V and make different Parzen window estimates. Okay. We can choose from many functions that satisfy these conditions. Then with the appropriate V we will get a density estimate, and all such methods all such estimates are called kernel density estimates, and the particular phi function you have chosen is called the kernel function for that particular density estimate. So, this is the general method of kernel density estimates. We essentially choose a phi function that satisfies these conditions, and we choose V to be this integral, then this estimate such a density estimate, this will be a density, and such a density estimate is called the kernel density estimate with the kernel function phi. For example, we can see at least one other phi function. Essentially we wanted phi to be a density. So, for example, I can choose phi to be Gaussian density. This is the d dimensional Gaussian density, right, 1 by root 2 pi to the power d exponential minus half u norm u square. This is essentially product of d one dimensional Gaussian densities. Okay. So, this is a Gaussian kernel or a Gaussian window. By simply finding that other integral, we can show that for this function also the appropriate volume will be h power d. Essentially, I scale each u by h here. So, then it will become u I square by h square. So, h will become the variance, h square will become variance. So, here I will get h root 2 pi. So, I will get a h power d term extra. So, that is how V will become h power d. So, with V is equal to h power d, this will be my density estimate. F at x is 1 by n is equal to 1 to n 1 by h root 2 pi to the power d exponential x minus x I whole square by 2 h square. Okay. As you can see, this actually product of n one dimensional Gaussians, each with variance h square. So, what we call the size of the volume element now is actually the variance of each of the x's. As you can see, this is actually a mixture density, right. We are essentially taking Gaussians centered at xi, that is each of our data points, and summing them, right. So, this is if I take 1 by n inside, this is sum of n terms, each one is 1 by n times a density. So, it is a convex combination of densities. So, this is a mixture density. We have considered such Gaussian mixtures earlier. So, instead of just choosing some Gaussian mixture and estimating it in an ML method to find the mixing coefficients and the the parameters of the individual Gaussians, here we are choosing exactly n Gaussians, where n is the number of data points, and centering each Gaussian at a data point, and keeping the Gaussians to have diagonal covariance matrix and the same variance, and keeping variance of all of them to be h, which is our control parameter for the size of the volume element. So, with this phi function, our kernel density estimate is essentially a mixture of Gaussians by adapting one Gaussian itself. Now, as you can see, it's no longer have the strictness of a unit hypercube window, because we are not really saying how many k actually fall inside this volume element, because now the volume element does not have a finite boundary, because Gaussian will go all the way up to infinity, but essentially we are erecting a Gaussian at each sample point and then representing our unknown density as a mixture of these Gaussians. So, this also comes under the same generalized histogram kind of idea, and this is another form for kernel density estimates. Very often one uses this because this gives us a much smoother density estimate. Our original Parzen window estimate, which used the unit hypercube, has discontinuities at the boundaries of the hypercube. So, that kind of introduce artificial discontinuities in my estimated density function, whereas this being sum of Gaussians gives me a very smooth density estimate. So, for example, very often the choice of kernel function for kernel density estimates is Gaussian, and one uses this kind of a nonparametric or kernel density estimate. Okay. So, now let us look at how such things work. See, now this is we have moved quite a bit away from the simple intuitive idea of histogram. We started with the histogram, then defined the window function to actually capture the histogram, then looked at the role that the window function is actually playing. We looked at what are the properties that function phi should satisfy. Then we realized that by choosing different phi, we can get very nice smooth estimates. Okay. Even though these are really counting estimates, they are quite smooth. So, now we can ask, do such estimates converge? By converge, what we mean is, if I get very large number of data samples, as number of data samples goes to infinity, does this estimate converge to the true density estimate? This is like the question of consistency of estimate that we considered in the parametric case. For example, we stated that maximum likelihood estimate is consistent in the sense as the number of data goes to infinity, I get back the true parameter values. In the same way, I can ask if the number of data samples goes to infinity, do the kernel density estimates actually give me the true density. Okay. So, let us look at this question next. So, we are looking at the convergence of these estimates. So, because we are looking at the convergence of these estimates, we have to ask what will be the estimate when I have n data samples, right. So, let f hat n denote the density estimate with n data samples, and similarly essentially if I want convergence, as n increases, I have to change the size of my volume element, okay, because if h remains constant, but number of data samples goes to infinity, it will not work. Last time we seen what we need as n tends to infinity. To get the true density estimate as n tends to infinity, I have to shrink the volume to 0. So, the h should shrink to 0. So, at different n I will use different h's. So, let h n and v n denote these quantities when the sample size is n. Okay. So, which means I am looking at a sequence of density estimates f at n x, this is what I will get if I have n samples, is 1 by n is equal to 1 to n, 1 by v n phi of x minus x I by h n. So, given that these are the sequence of density estimates I am getting, the question that we want to ask now is, does this f hat n converge to f? Of course, this question converge is a little difficult here, because f hat, as you can see, is a function of x I, and x i's are IID sample, they are random. So, f hat n is random. So, this is a sequence of random variables f hat n x. So, I have to specify in what sense is this convergence to be understood, and like in the consistency definition earlier, we want to think of this as convergence in probability. Okay. So, we need a little more notation. Let delta n x represent 1 by V n phi of x by h n. Okay. Essentially, if I think of this as a function, its amplitude is 1 by V n, okay, and its width is determined by h n. So, as I change h n, the width changes and also V n changes, so the amplitude changes. Essentially, for both the functions, both our hypercube window function as well as the Gaussian function, as h n becomes smaller and smaller, the width reduces, whereas 1 by V n increases, the amplitude goes up and the width reduces. So, both the amplitude and width of delta n are affected by h n, and for both these functions, as the width sinks to 0, the amplitude goes to infinity. So, we assume that as n tends to infinity, we have our h n goes to 0 in such a way that delta n tends to the delta function. Okay. We said as n tends to infinity, we have to let h n go to 0. So, it is saying h n should go to 0 in an appropriate fashion. So, that this function delta n tends to a proper Dirac delta function. For both the phi we consider, both the hypercube function as well as the Gaussian function, this is true. So, if we simply let h n go to 0 with n, then as h n goes to 0, as n tends to infinity, delta n tends to a proper delta function. Okay. Now, having defined delta n, we will write our estimate f hat n in terms of the delta function. Now, one more property of the delta function that we are getting is, we have defined V n to be this integral of phi x minus x n by x I by h. So, 1 by V n phi x minus x I by h n dx is always 1, which means delta n x minus x I dx is 1 for all I all n, right. So, this is another property of delta function, which ensures that as n tends to infinity, this delta n converges to a true Dirac delta function. Okay. So, we can write f hat in terms of delta n as f hat n earlier is 1 by n, 1 by V n phi x minus x I by h n. I said earlier, the reason I kept this 1 by n outside as a purpose, that is because now I can put this as delta n, right. I can write this as 1 by n delta n x minus x I. So, this is my estimate in terms of delta n. Okay. Now, as we already discussed, f hat n is random variable, f hat n x is a random variable, because it depends on these IID data samples which are random x I. So, this is a random variable, that is a function of this x I, and let us also remember that x I are IID and each x I has density f, the unknown density. Okay. The f is what we do not know and we are estimating with f hat, and each of these x i's are IID according to f. Okay. Both these facts are useful to us in ultimately obtaining the convergence. To obtain the convergence, we have to ask, is f hat n x converges in probability to f x. For that, what we look at is what happens to the mean and variance of f hat n x tends to infinity. Okay. Let f hat n x be the mean, the bar f bar n x be the mean of f hat n x. Okay. So, f hat n x is expectation of f bar n x is expectation of f hat n. So, expectation goes inside the sum, put it there. What is inside this expectation is a function of the random variable x I, and x i's are IID. So, this expectation has the same value for each I, and so I am summing them and dividing by n. So, this entire thing will have the same value as expectation of any one of these terms. Okay. Now, expectation of any one of these terms is easy to write, because in this expectation what is random is this x I, and I know the density of x I, no meaning I know the symbol for the density of x I, x I are x I of density f. So, I can write this entire expression as integral 1 by V n phi of x minus z by h n f z d z, because this x I is the random variable which has density f. So, the expectation inside is given by this integral, as you said x I are I I d. So, each of these expectations are the same value, and then I divide by 1 by n. So, both 1 by n and the summation will go, and the f bar n x will become this. Now, we already have a symbol for this, this is delta n, right. So, I can write this as delta n x minus z f z d z. So, I know that f bar n x, which is the expected value of f hat n x, is given by integral delta n x minus z f z d z for all n. Okay. So, now to ask what happens to the mean as n tends to infinity, right, we have to ask what happens to this as n tends to infinity, right. So, we have this, and as n tends to infinity we know that delta n becomes the delta function. When delta n becomes the delta function, integral delta x minus z f z d z will be f x, that is the property of the delta function. Right. So, because we know as n tends to infinity delta n becomes the delta function, this equation tells us that as n tends to infinity f bar n x, which is expected value of f hat n x, goes to f x. So, as n tends to infinity, the mean of f hat n x goes to f x. So, if I can show that the variance goes to 0, then this means f hat n x converge in probability to f x. So, now that we know that the mean converges to f x, let us look at what happens to the variance of f hat n x. Okay. The f hat n x is given by I is equal to 1 to n, 1 by n, 1 by v n phi x minus x I by h n. I just put 1 by n inside for a purpose. So, f hat n is the sum of some n terms, each one is a random variable, right, is a sum of n terms, each a function of x I. Okay. Now, x i's are independent. So, this random variable is sum of some n random variables, they are independent, each of these are independent, because for different I these are functions of different x I, and hence they are also independent of each other. So, f hat n x can be represented as sum of n independent random variables. Since x I are independent, variance of f hat n would be sum of variances of these n random variables. So, essentially to find f hat n x I have to find variance of each of these and sum them up. Okay. Now, each of these are I I d, this each term is dependent on the random variable x I and the same function, they are all the same functions of x I are I I d. So, the variance of each of them would be same. So, variance of f hat n will be n times variance of any one of them. Okay. To find variance, I have to find variance of any random variable z is expected value z square minus expected value z whole square. So, I need to find the expectation of each of these and then also expectation of square of each of these. First, let us look at the expectation. The mean of f hat n, which we called f bar n x, is I is equal to 1 to n expectation 1 by n of this. Now, we know that this is equal to f bar. Now, each expectation is same and sum of n of them is equal to f bar. So, each one of them is 1 by n f bar. So, hence the each expectation inside the sum is 1 by n f bar n x, right, which means each of these random variables have mean 1 by n f bar n x, and we need to find the variances of each of them and sum them up. Okay. And of course, we do not have to sum them up, each of them are the same variance. So, we take n times variance of any one of them. Okay. So, if we think of sigma square n as the variance of f hat n x, then we can write sigma square n as n times variance of this, right. I just said f hat n x is sum of these n things, each of them are the same variance. So, variance of f hat n will be n times variance of each of these. Okay. So, sigma square n will be n times variance of 1 by n 1 by v n phi x minus x I by h n, where x I is the random variable with respect to which I am finding variance of this term. Okay. So, what is variance? Expectation of this square minus expectation of this whole square. Expectation of this we already know is 1 by n f bar n. So, I can write this as n times expectation of the square of this 1 by n square 1 by v n square phi square x minus x I by h n minus expectation of this whole square, once again n times expectation of each of them is f n by n. So, square is f bar n square by n square. Okay. So, that is sigma square n. Now, this term is always positive, n into 1 by n square into f bar n whole square. So, sigma n square is this minus this. So, if I drop this term, right, sigma n square I get the okay. Before I drop the term, let me write as well, first get this expectation out. This is expectation of this, where x I is the random. So, I can write this as this n will cancel with one of these n's. So, I can take 1 n v n out, I get 1 by v n phi square x minus z by h n f z d z, because each of the x i's are IID with density f. So, expectation of this is given by this expectation integral. The integral is over R d minus this is 1 by n f bar square n x. Now, given this, as I said, sigma square n is this minus this, and this is always a positive term. So, if I drop this, I can write sigma square n is less than or equal to 1 by n times v n integral 1 by v n phi square x minus z by h n into f z d z, right. The same thing, the first term alone. The reason for writing it like this is that 1 by v n phi x minus z h n f z d z is something we already know, that is f bar n. Okay. So, what I can do is I can take 1 phi out. So, this is phi square x minus z. If I want to take 1 phi out of the integral, I can substitute it with the maximum possible value phi can have. Let us call it supremum of phi. Supremum of phi is max over u phi u. For all the window functions we consider, this is finite. So, if I take that out, so 1 phi I have taken out, I left 1 by v n phi x minus z by h n f z d z, and we have already seen this integral. So, that will give me f bar n, right. That is how the mean of f hat n is defined. So, what I get finally is supremum over phi f bar n x n into v n. F bar n x is finite, okay. This the mean of these random variables, supremum phi is finite. As we have seen, the way we let these sizes go to 0, in the previous class we said we have to have n v n should go to infinity, right. So, as n tends to infinity, sigma square n becomes 0, right. So, we have sigma square n less than this, and this implies sigma square n goes to 0 as n tends to infinity. So, what we have shown is as n tends to infinity, the mean of f hat n x at any given x becomes f of x, and its variance goes to 0. So, as we get large samples and we choose our volume element h n, so that h n goes to 0 as n tends to infinity in such a way that this n v n goes to infinity. See, as h n goes to 0, the volume element shrinks to 0, but we should shrink it in such a way that n times v n should go to infinity. So, if we let our h n go to infinity in the right way, that means we choose our h correctly as n tends to infinity, then we can show that f hat n x are such that as n tends to infinity, its mean becomes f of x and its variance goes to 0, thus showing that f hat n x converges in probability to f x, right, and that tells us that kernel density estimate is a consistent estimate. Okay. So, to sum up, we came up with kernel density estimates by starting with the simple intuitive idea of a histogram. You simply cut your space into bins and count how many points fall in it out of n. Then using binomial theorem and assuming that the density is constant over each of the bins, we can get a very simple formula for estimate, that is f at n is k by n v n, where v is the volume element, n is the total number of samples and k is the number of samples that fall in v. Then we seen how we can write this using a proper window function. We first started with a rectangular window function, which is the Parzen, so called Parzen window, that exactly counts like this, and then written out our f hat and x, and that showed us that we if we have that phi function and all the xi with us, we can simply compute f hat x at any x that we have. It also showed us that that window function we can choose any other window function instead of a simple hypercube window function, and essentially as long as we keep phi as a density function, it will work. Then we generalize it to a kernel density, which is essentially a mixture density form, where we erect one density centered at each of the sample points. For example, when we use the Gaussian function at the kernel, when we use the Gaussian kernel density function, kernel density estimate is such that at each of the sample points xi, we erect a Gaussian and then take a uniform convex combination of them as our density estimate. Okay. That is the kernel density estimate, and for that kernel density estimate we showed, just like our other parametric density estimates, that the density estimate is consistent. That is, as the number of samples goes to infinity, we get the true estimate. Of course, at any finite samples we have to know what h to choose, but at least it is nice to know that asymptotically it is a consistent density estimate. Okay. So, kernel density estimates are essentially mixture density estimates. Okay. We store all the data samples, right, and then compute the density wherever needed. Essentially, depending on how many data samples we have, for example, if I have n1 data samples, so we erect n1 such densities, each density centered at one of the data samples, and then do this mixture density estimate. In general, one particular form for kernel density estimate that is often preferred is the Gaussian kernel, and the idea is that we do not have to store any density estimate formula, we only know the formula for phi, and we store all the data samples xi, and given any x, whenever we need to compute f hat, we compute it using this formula, okay, for any number of samples we have. That is why I changed n to n1 to say that in practice we may have some specific number of samples. So, we cannot use the asymptotic estimate, that is why we used a fixed v and fixed h. Okay. Now, kernel density estimates are easy to use, so you simply store all the xi and you can compute it at any x that you need. However, computations could be expensive. When I want to compute f hat x, I need to compute all these phi's. So, if I have n1 data samples in one class, and if each of the phi's are Gaussian, given any particular x, if I have to compute f hat x, I have to actually compute n1 Gaussian functions, okay, because Gaussian function has an exponential in it, that is the most expensive computation. So, I have to actually compute n1 Gaussians if I have n1 data samples. Okay. Data samples could be in hundreds. So, this is a non-trivial amount of extra computation. So, computationally they are expensive. So, as I said, in particular if I have two class problem with n1 data samples from one class and n2 data samples from the other class. So, to compute the first class 1 class conditional density, I need to do n1 phi computations, and similarly for the class 2 density I need to do n2 phi computations. So, if we use a Gaussian window function at any given x, we need to compute n Gaussians, right. On the other hand, if it is feasible to use a density model, if it is feasible to assume that the classical initial densities are Gaussian, then the computation is very simple. If we can model both classical densities as Gaussian, the needed computation is much less. We need to compute only 2 Gaussians, right. So, kernel density estimates are expensive. Obviously, we will go for such expensive estimates only if we feel that no simple density model will work for these classical initial densities, right. So, if the classical initial densities are such that we think we can model them with Gaussian or mixture of 1 or 2 Gaussians, it is always good to model them like that. Only if we think that the classical initial densities can vary very much, they are very heavily multimodal, that is when we use kernel density, and then obviously we can't complain about the extra expense because the problem is difficult. Another issue with kernel density estimate is the size of the volume element. As I said, the choice of H is critical. At any given time we have only finitely many samples. So, I have to choose a particular H, and there are no simple rules to say which H is reasonable for a given sample size. Also, the same value of H may not be good at all points in the feature space, right. Because the classical initial density is obviously not uniform over the feature space. At some places the density will have high value, some places will have low value. So, in our sample set also we get many more samples in certain regions of the feature space and very few samples in some other regions of the feature space. So, using the same H throughout the feature space may not also be a good idea, but on the other hand we do not know how to vary it, right. One can choose different H in different parts of the feature space, but once again what rule do I use to adopt H like that? One method is to say that if I want the density at a particular point x, if there seem to be too many samples around that x, then I can use a small h, otherwise I can use a big H. Okay. This goes a little bit like the k nearest neighbor estimate. There are a few heuristics to do such adaptive choice of H, but there are no well grounded, theoretically well grounded rules for this. In spite of all these problems, in spite of its computational cost, in spite of the difficulty in choosing H, kernel density estimate are still the most popular non-parametric estimates, because if I want to do a non-parametric estimate, I will go for a non-parametric estimate only when the problem is difficult and I cannot easily capture the density model, in which case kernel density estimates are about as good as one can get. Okay. But anyway, we have another method, as we said, the k nearest neighbor approach. So, let us briefly consider this also. Generally, k nearest neighbor approach is not so much preferred for density estimate. Very often it is preferred more for regression problems where I want to do a function estimate, but any case its nice thing is that we do not have to choose H. Instead we have to choose K, which at least intuitively looks much easier. I want to know how many nearest neighbor samples should I rely on. Should I have 1, should I have 3, should I have 5, that might be a little more easier to guess. Okay. So, we choose a K and find a volume to enclose K, and that is how we get the nearest neighbor estimate. Okay. Once again the estimate is same, K by NV. So, we first choose K. So, given an x, I will ask where is the kth nearest neighbor, and I draw a sphere, a hypersphere to just enclose the kth nearest neighbor. Its radius will be the distance from x to the kth nearest neighbor, that will be the value of V, and then this will be my nearest neighbor k nearest neighbor density estimate. Okay. What we would like to consider in this is one interesting relationship between such a nearest neighbor density estimate and the nearest neighbor classifier. If you remember, in our second class we considered a simple classifier which we call the nearest neighbor classifier. What does the nearest neighbor classifier do? It just stores all the xi, all the training samples, then give it any nu x. From the training samples it finds what is the nearest training sample to x, and if the nearest training sample to x is in class 1, I put x also in class 1, if the nearest training sample is in class 2, I put x also in class 2 and so on. So, that is the nearest neighbor. The k nearest neighbor classifier is, instead of finding one nearest neighbor, I find the k nearest neighbors of a sample and then ask the majority class. I ask which are the let us say out of the k nearest neighbors, k I are in class I am asking for which I k I is largest, right. So, if of the 5 nearest neighbors, if 2 are in one class and 3 are in the other, 3 are in class 2, then I will put x also in class 2, that is what k nearest neighbor is. So, the nearest neighbor density estimate is closely related to the nearest neighbor classifier. Let us say we have a 2 class problem with prior probabilities p I and class conditional probabilities f I is equal to 0 and 1 that is p 0 p 1 are the 2 prior probabilities, f 0 f 1 are the 2 class conditional densities, and then f x is p 0 f 0 plus p 1 f 1 is the overall density of the feature vector x, right. This is the without the class label, this is the overall density of the f x. Suppose there are n data samples of both classes, of out of which n 0 are from class 0 and n 1 are from class 1. Okay. Let us say we do k nearest neighbor estimate of f, the overall density. So, in the overall density do not have to consider class labels. So, I have got n data samples and I want to estimate the overall f, and suppose at a particular x for the k nearest neighbor estimate the needed volume element is v. Suppose in this volume in which I know there are k neighbors of x, k I of the neighbors are of class I. So, k 0 from class 0 and k 1 from class 1. Okay. Now, let us say using the same v I can now estimate f as well as f I, because for f I have n I samples of which k I are in this volume, and for f I have n samples of which k are in this volume. So, using the same volume I can simultaneously estimate f 1 as well as f 0, right. Let us suppose we do this estimate, then what will be f I hat? K I out of n I or in this volume v. So, is k I by n I v, and f hat is k by n v, because k out of n are in this volume. What will be my prior estimates? P I hat will be simply n I by n, because P 0 hat will be n 0 by n and P 1 hat is n 1 by n. This is the simple Bernoulli estimate for priors. Now, let us say using these estimated priors and class conditional densities, we want to calculate the posterior probabilities. So, posterior probability q j using the estimated quantities is f hat j p hat j by f hat j x p hat j x by f hat x. So, substitute for this f hat j will be k j by n j v, p hat j is n j by n, and 1 by f hat x will be n v by k. Now, these n j's will cancel, v's will cancel, n will cancel, this will simply become k j by k. So, what does this mean? So, if we want to implement Bayes classifier, x would be put in class j if q j x is greater than q x, right. Let us take 0 1 loss function for simplicity. So, if the posterior probability of class j is greater than posterior probability of class I put x in class j. Now, q j x greater than q x same as k j greater than k I. What are k j and k I? Out of the k nearest neighbors of x, k I are in class I, k j are in class j. So, if class j neighbors are more than class I neighbors out of k. So, out of k neighbors, if jth class is the majority class, that is what k j greater than k I means, then Bayes classifier says put it in q j. So, if I use a nearest neighbor density estimate and use that estimate to implement Bayes classifier, then what I get is the nearest neighbor classifier, right. As a matter of fact, we do not have a complete the nearest neighbor density estimate also we can study asymptotically. If you study asymptotically like that, one can actually show that the nearest neighbor classifier has a very interesting property, that its error rate will never be more than twice that of the base rate. So, if base error is p star, then the error rate of a nearest neighbor classifier p will be less than twice p star asymptotically. That is, as the number of samples goes to infinity, the nearest neighbor classifier worst case error rate is always bounded above by twice the base rate. Okay. That comes because essentially the nearest neighbor classifier is the base classifier implemented through this kind of density estimates. Okay. That is a very interesting thing, because if I think optimal base error is, let us say 5%. So, if I had actually estimated my class conditional densities exactly and implement base classifier, I expect to get 95% correct, and essentially doing nothing, just doing a nearest neighbor classifier, I can hope to get 90% accuracy. So, this is another reason why nearest neighbor classifier is always used as a benchmark to see whether a complicated classification method is needed in a given application. Okay. So, but anyway, more to the point, in our current context, essentially the k nearest neighbor density estimate is such that if we use such density estimates and implement the base classifier based on such a density estimate, what we get is the k nearest neighbor classifier. So, now let us sum up. Almost for the last 7-8 classes, we have been considering issues involved in implementing the base classifier, right. So, all these last 7-8 classes or a little more, we have been discussing essentially implementation of base classifier. The idea is that base classifier is optimal for minimizing risk. If you give me the class conditional densities and right probabilities under any loss function, base classifier is the best risk. Okay. So, that is the reason why one would like to implement base classifier, but to implement it we need the class conditional densities, right, because we do not know the class conditional densities. The idea is that class conditional densities can be estimated if I have got IID samples from each class. The idea is for each class I have taken the IID samples. So, now the problem reduces to given some density f which is unknown, but I have an IID sample from the density, can I estimate the density. So, the idea is with given the density estimates we can implement base classifier, and as we said we can estimate densities either parametrically or non-parametrically. So, we have looked at both methods. In parametric method we assume a form for the density and estimate the parameter, that is we assume density to be let us say Gaussian, but we do not know the mean and covariance matrix, or we assume the density to be in the discrete case a geometric, but we do not know the parameter p and so on. Then the idea is given the IID samples you estimate the parameters. We looked at two methods of parametric estimation, maximum likelihood and Bayesian methods, right. We seen that both of them are give us consistent estimates, and essentially Bayesian methods allow us to use any extra information we have about the unknown parameters at the cost of a little more complicated analysis for deriving the estimates using the so called conjugate priors. Also they allow us to get better estimates at small sample size. At large sample size both maximum likelihood and Bayesian estimates are same. We also considered estimation, we considered maximum likelihood and Bayesian estimation techniques for all the standard densities, essentially the exponential family of densities, and we also looked at mixture density models which are more general, which can model which can capture multimodal data distributions, and we looked at an EM algorithm, a specialized algorithm for ML estimation of any mixture density model. Then we also looked at the non-parametric method, where we do not know the form of the density, we are not willing to assume any form for the density, but we still need a density estimate. And in last class and this class we seen some ways of looking at such density estimate, mainly the so called kernel density estimates. Okay. And we also looked at the nearest neighbor density estimates and seen their relationship with k nearest neighbor. So, this kind of completes one aspect of our pattern recognition journey. So, we started with a model, the statistical pattern recognition model, whereby we said the variabilities in feature vectors belong to the same class are modeled as densities. Then we derived the Bayes classifier. We seen how we can rate different classifiers using minimization of risk through a loss function, and we showed that if we know the class conditional densities and priors, Bayes classifier will give you the minimum risk. And then we also looked at a few other classifier structures. Then we come back to implementing Bayes classifiers, and for that how to use the training samples for estimating the density functions. So, with the estimated density functions we can now with estimated density functions we can implement the Bayes classifier. The issue with Bayes classifier is optimal only when we exactly know the posterior probabilities. When we estimate densities, of course, there will be inaccuracies, and because of the inaccuracies the implemented Bayes classifier will be non-optimal. So, even though the Bayes classifier is best, any implemented Bayes classifier will not be optimal anyway, because there will be inaccuracies in density estimates. So, as we discussed in one of our beginning lectures, the second lecture, there are other approaches to classifier design, which we called for example, the one based on discriminant functions. Okay. So, beginning next class we will look at the discriminant function based approach. Okay. So, we kind of now completed the implementation of Bayes classifier and all the discussion based on that, and now we move on to other ways of looking at. So, we will first look at implementing linear classifiers, essentially linear discriminant function based classifiers, and the associated regression function estimates, both for linear models first, and once again using a risk minimization strategy. That is what we will do starting from next class. Thank you.